Hello, everyone. Today I'm going to talk about the swimming dynamics of a magnetically controlled soft robotic system, and we're going to investigate the mechanism as well as the factor that affect the locomotion of the system. Before we start, I would like to give thanks to my advisor, Ashar Kudroli, and Julian Chopin for assisting me with this project. The motivation for this project is the uncoformed swimming from a variety of organisms in nature. We are interested in the proposed stiff force generated by the transverse annulation of the organism. Um, so as you can see here, it's the Lumbriculus variegatus, the C. elegans, and the eels. Previously, we have seen that the Californian blackworms move faster in sediment compared to water. However, the activities of these worms are unpredictable. Um, because of that, we need a simplified and controllable system to model this form of locomotion. So in our lab, we fabricated a swimmer with a magnetic head attached to an elastomer body, which explored the biomimetic principle of these organisms. And with this robot, we can control the applied driving frequency, also the material properties and the viscosity of the medium, and learn which affects the form of locomotion. So speaking of the making of the robot is comprised of two parts, the magnetic head and the elastic body. The head is made from a strong neodymium magnet, and this will drive the entire system. The body is made from a type of polyvinyl elastomer, and we make three versions of these robots. Each will have a different elasticity. From top to bottom, we can see that the pink one is the most flexible one, and the green one is the most stiffest one. Here is the schematic of the construction of the robot. With these version has similar mass and identical dimension, therefore the central amount of these versions are virtually similar, which is about 10 millimeter away from the head. The fabrication of this swimmer is simple and straightforward. The body is molded with a syringe needle, and a disc magnet is glued to the elastic body. So there are two environments that we are interested in testing our swimmer. First is water. For the water case, we just use regular tap water, and the water is at the room temperature, which is 24 degrees Celsius. Next is the granular hydrogel. The diameter of the hydrogel is about 0.5 to 2 millimeter in diameter and has the density is close to that of water. So these hydrogel particle is neutrally buoyant in water. For the hydrogel bed that we set up, the bed is 5 to 20 millimeter in depth, and the sediment bed is stirred frequently and left to fully settle after each trial and before starting a new trial of experiment. So this is an illustration of how the bed will set out to be. The hydrogel bead, the reason why we use hydrogel is that the hydrogel beads has similar refractive index as water, so we can see through the sediment bed and capture the motion of the robot inside of the sediment. So now let's talk about the experiment setup. First, the setup has the light source beneath the container with our magnetic robot swimmer inside. Then we have a pair of Helmholtz coil on both sides of the container. Finally, we have a high-speed camera attached from above this entire setup to capture the motion of the swimmer. Within the setup, an alternating current is applied to the pair of Helmholtz coils. Therefore, we generate alternating magnetic field inside of the environment. the neodymium magnet will experience an alternative torque with the same frequency as the applied current. As a result, the magnetic head rotates and transfers the energy to the body. We use an oscilloscope to control the frequency of the current applied, and the driving frequency is ranging from 1 hertz to 10 hertz. So now let's look at the swimming speed of a robot. The Reynolds number, which help predicts the flow pattern of different fluid in different flow situation. At lowest Reynolds number, the flow tends to be dominated by laminar sheet-like flow, while at high Reynolds number, the flow tends to be turbulent. The Reynolds number is measured for both water and sediment case. We can see that the Reynolds number is much higher for water compared to the sediment case. Consequently, we notice that the swimmers swim faster and move forward easier compared to this in water compared to the sediment case. And it is evident as we look at the video in comparison, as well as the tracking of the swimmer in 1 second time interval. It's clear that for the same amount of time, we can see that the swimmer cover more distance in water compared to sediment case. And notably, at 1 hertz, the robot oscillates in place and does not move forward. And moreover, we can see that in both cases, the pink swimmer, which had the most flexible body, swim considerably greater than considerably faster than the other two swimmer, which begs the question like, how's the swimmer different than the other two? For that, we look into the body deformation of the swimmer, and we notice that the shape of the robot changed from a rigid body rotation to an anguilliform shape. So as you can see right here, at 1 hertz, there appears to be no curvature along the body. However, as we increase the frequency to 4 hertz, we can see that the body bends quite a bit. And the deformation increase as we apply higher frequency to the system. On the other hand, the deformation remained constant in the sediment case as we increase past a threshold frequency. This can be explained by the fact that the viscous force in the sediment is higher than water, so the robot would struggle to move side to side in the sediment. And in both cases, the most elastic version of the swimmer has the most deformation. Also, we notice that the elastic swimmer with the greatest deformation has the benefit of the anisotropy, which increase its swimming speed as seen before. So this is a supplementary experiment where we discuss the drag anisotropy of the solid body. The drag anisotropy is the ratio between the perpendicular drag and parallel drag relative to its cylindrical axis. Without this, the linear translation would be impossible. We drag a thin rod in the sediment in two different orientations. The rod is connected to a torque sensor. As it drags through the medium, the torque sensor will pick up the signal and we can measure the drag force this way. We observe that the perpendicular force on the drag is consistently greater than the parallel force. As we bring the rod closer to the bottom of the container, the drag force on the rod subsequently increases as well. By fitting the data to a linear approximation in plot C, we find that the drag anisotropy as a slope of these lines. We found that the drag anisotropy increased as we place the rod deeper in the sediment bed. We also measure the effective viscosity from this relationship between the perpendicular force and the effective viscosity, we can observe that the viscosity is greater for lower dragging speed and then decrease as we increase the dragging speed. So it's this is a modeling work from our collaborator Julian Chopin. The swimmer is modeled after a dam elasto-hydrodynamic equation right here. In this model, we simulate a swimmer which is torque driven at the head and free at the other end within a non-Newtonian rheology. We use the effective viscosity to measure the swimming speed calculated by the resistive force theory. As a result, we have a model that resembles to our collected data. So to wrap this up, we have three main takeaways. First, the speed of the robot is dependent on the medium of the medium and the elasticity of the swimmer. And as we observed before, the most elastic swimmer swim the fastest in both water and hydrogel sediment. And systematically, we see that all swimmers swim faster in water compared to hydrogel. Meanwhile, the shape of the robot changed from a rigid body rotation to an angular foam shape. The increase in anisotropy also increased the increase in the anisotropy also increased the swimming speed of the robot. And third, the dragging force on a slender cylinder increased as we go deeper into the sediment bed. Thus, for the swimmer at the bottom of the sediment will experience great drag forces. Also, we have developed a model that capture the trends of the swimming speed through the elasto-hydrodynamic model. Yeah, this is the end of my presentation. Thank you for listening, and I hope you enjoy this talk.